All right, so let's talk about these electron configurations I've mentioned a few times. Electron configurations tell us how the electrons are arranged in the orbitals of multi-electron atoms. So now we're talking about these multi-electron atoms. Electron configurations can clearly still go with hydrogen and single electron atoms, but they're not very exciting. So we're going to mostly talk about multi-electron atoms here. So I've mentioned this before, but we didn't have it explicitly defined. So the Pauli exclusion principle states that uh, these electrons, if they're in the same orbital, have to have opposite spins. And more generally, it states that sorry, let me get my pen up here. And more generally, it states that each electron must have a different combination of the 4 quantum numbers. So this is a pictorial description of that. We can't have 2 electrons with the same spin in the same orbital. So the orbital is defined by these 3 things, specifically by m sub l. And then those 3 numbers can all be the same, but if they are, the m sub s has to be different for the 2 electrons. One has to be up and one has to be down. We have to have opposite spins. That's what the Pauli exclusion principle tells us, that each electron must have a different combination of the 4 quantum numbers. So let's look at an analogy here. So N identifies the shell of the electron, the energy and the size of the electron's orbit. L identifies the subshell, the shape of the orbital. M sub L identifies the orbital itself. So if we're talking about S, it's the same as the subshell. If we're talking about P, then L identifies that we're in subshell P, but M sub L identifies that we're in 2px or 3py. It identifies the specific orbital within the subshell, and m sub s identifies the individual electron in that orbital. So if we look at an analogy here, it's like the shell is the city you live in. Then we have to narrow it down a little bit. The street that you live in is the subshell. So the street is within the city. And then on that street, it's your house. So the house is on that street in that city. So it's kind of we're narrowing down our location. We're getting a more precise idea of the location of the electron. And finally, the person in the house is the electron. So for example, your mom and dad or your roommate and yourself. So M sub S identifies the individual electron. It's like identifying the individual person inside the house. All right, so let's look at an example here. For example, the quantum numbers n equals 3, l equals 2, m sub l equals 1, and m sub s equals positive 1/2 identifies an electron as an up spin electron. We got a positive 1/2. It doesn't really matter if it's positive or not. It's just an up spin or a down spin, an up arrow or a down arrow, as we will be drawing them in our electron configurations. So it's that electron in one of the 3D orbitals. So the n equals 3, the l equals 2 tells us it's the d orbital, and m sub l just tells us that it's one of those orbitals. We don't know the correlation between the value of m sub l and which one of the orbitals it is, but we just know it's an electron in one of those orbitals. So let's look at our possible values for things, or how many orbitals. So we learned how many orbitals there were, how many m sub l values there were for each subshell in the last section. And now we're going to refine it a little bit more. There's 2 electrons in each orbital. So for each value of n, there's only one s orbital. And it has 2 electrons. Or it could have 2 electrons. That's the max. For each n, there's 3 p orbitals. If we're at n equals 2. At n equals 1, we don't have p orbitals. But n equals 2 and up, we have 3 p orbitals. And because there's 3 orbitals, we have a capacity, I should say a capacity of 6 electrons. Not that they have to be containing that many electrons, but that's the capacity, I would say, for those orbitals. So we're looking at subshells, I would say. So the number of electrons that could be in this subshell. There's a possibility for 6 electrons in the p orbitals, so the p subshell. And then there's 5 d orbitals with 10 electrons total, and 7 f orbitals with 14 electrons total. So here we have to be n equals 2 plus. Here we have to be n equals 3 plus. And here we have to be n equals 4 plus. And if you don't remember why, you should take a look at the last lecture video because you should know why. We learned about the values of n and how they correspond to the different subshells. All right, so those are our capacities. So if we look at a shell, say we look at the n equals 3 shell, there is an s orbital in that shell. So then there could be 2 electrons in that s orbital. The n equals 3 shell also has 3 p orbitals. So there could be 6 electrons in those p orbitals. And when n equals 3, we can also have d orbitals. We can have L equals 2. So there's 5 d orbitals and 10 electrons total. So that's it for the n equals 3 shell. We need n equals 4 or more to get to the f orbitals. So in this shell, there could be a total, there's a capacity for 18 electrons. Okay, if we look at the n equals 2 shell, we can't do the d orbitals. So for n equals 2, just write it up here, we have a capacity of 8 electrons, 2 from the s orbital and 6 from the p orbitals. And when we have n equals 1, we can only have these 2 electrons possible. So the capacity of our shells is increasing as n increases. Okay, good to know. All right, so let's talk about this electron configuration thing. So now that we know about our quantum numbers and their values and how they correspond to exact electrons, let's look at electron configurations. So electron configurations are often represented this way. So the N is the number, the L corresponds to the subshell, so S, P, D, or F. We call this SPDF notation. And then there's a number, a superscripted number that tells us the number of electrons in that orbital or subshell. So we can look down here. So like I said, the number at the beginning denotes the principal quantum number n. The S denotes the type of orbital or subshell, which is determined by L. And then the number, the superscripted number, denotes the number of electrons in that orbital or shell. So let's look at helium, for example. It's our first multi-electron atom that we can look at. So it's got 2 electrons, and the way that we write the electron configuration of helium, the way that those electrons are arranged in the orbitals of helium is 1s2. So this guy was 1s1, That corresponds to hydrogen because there's only one electron. 1s2 corresponds to helium because we're still in the n equals 1 shell. We're at the top row of the periodic table, the first period. Because n equals 1, L has to equal 0, which means we're in an s orbital. And helium has 2 electrons when it's a neutral atom. You can tell because the number of electrons equals the number of protons in a neutral atom, which we learned in chapter 2. So helium is atomic number 2. It has 2 protons and 2 electrons. So those 2 electrons are in the 1s orbital, and we write the electron configuration as 1s2. Okay, so then we also have orbital box notation. So this is another way to write it, where we have the 1s orbital drawn as a box, and then we drew the 2 electrons in the box. So for the upspin electron, we've got n equals 1, L equals 0, m sub L equals 0, and m sub s equals positive 1/2. And then, because we have 2 electrons in the same orbital, the other one has to have m sub s equal to negative 1/2, because we can never have 2 electrons with the same combination of those 4 numbers. M sub s has to be different if we have 2 electrons in the same orbital. So when we have 2 electrons in the same orbital, that means the first 3 numbers are the same. So the last one has to be different. Cool. All right, so now we're going to talk about something called the off-bal principle. The off-bal principle tells us that when you're writing the ground state electron configuration, the lowest energy state for that atom. So we learned about the ground state of hydrogen, where n equals 1. Now we're going to talk about the ground state electron configuration for many electron systems. So when we have more than one electron, some of them are not going to be n equals 1, but they are all going to be put in orbitals to minimize the energy of the system for the ground state. So when writing the ground state electron configuration, you fill the orbitals in order of increasing energy. So this is where our n and L values come in. I didn't make that one a cursive L. Oops. So based on the n and L values for the atomic orbitals, the order of increasing energy, or the order of filling, we call it, is this. So this is only up to the 4s row of the periodic table, or the 3D electron configurations, but it's a start. So the order of filling is 1s is filled first, then 2s, then 2p. So that follows our expectation for the hydrogen atom as well. But then 3s and 3p, still following that increasing n, increasing L concept. And here at 4s and 3d, we get our first weird spot where the 4s orbital is less than the 3d orbital in energy. So we fill the 4s orbital first because it has a lower energy than the 3d orbital. We don't want to put an electron in the 3d orbital until we have to, until we've run out of other orbitals to put it in that are lower in energy. Okay, and this little diagram over here is another way of representing that. So we fill the 1s first, the 2s, and then the 2p and 3s, and then the 3p and 4s, 3d, 4p, 4s. So now it starts to get more and more split. We get more splitting, more overlapping of orbitals. So I'm just going to write the first 5 there. But this is our order of filling. We do this diagonal line first, this diagonal line second, this diagonal line in this direction third, this diagonal line fourth, and then this diagonal line fifth. So that is our order of filling. 1s, 2s, 2p, 3s, 3p, 4s, 3d. So you want to go one diagonal at a time. So the first diagonal, then you drop down to the next diagonal, then you drop down to the next diagonal, and so on and so forth. But what happens when we have different 3p orbitals or different 4s, sorry, not 4s, different 4d orbitals, so on and so forth. The p, d, and f subshells, or p, d, and f orbitals, are something called degenerates. So they are degenerate in energy. So when they have the same n value, like 2p, then all three of the 2p orbitals are degenerate in energy. Traditionally, we write the first electron in those orbitals as the electron in the first box, but it doesn't matter because they're all the same energy. We could have easily written it over here. It's just tradition. And then the d orbitals are the same. So we've got 5 d orbitals for each value of n, and they're all the same. So this is like the 4d. Those 4d orbitals are all equal in energy. So if we have one 4d electron to put, it doesn't matter where we put it. Okay, same with the f orbitals. So these orbitals are degenerate. They're all equal in energy. So that's why they don't have different designations over here on this diagram that teaches us about filling the orbitals. They're just boxes that correspond to all of the p orbitals, all of the d orbitals, all of the f orbitals, like 4f. There's 7 different orbitals in there, but they're just drawn as this one little box. And this is boron, our first example of having to fill p orbitals. Boron is atomic number 5, so it's got its first 2 electrons in the 1s orbital, its next 2 electrons in the 2s orbital, because we're filling in order of increasing energy. So we got 1s2, 2s2, and then we get to the 2p orbital because we have one more electron to do something with. So that last electron is going to be a 2p electron. It's going to be in a 2p orbital, but we don't know which one. It can be in any of them because they're all equal in energy. So we would write the electron configuration of boron if we put it all together as 1s2, 2s2, 2p1. Okay, cool. One more rule for you. So Hund's rule of multiplicity states that when there are multiple electrons in the same subshell, they should be unpaired if we have enough orbitals to do that. So this is carbon. Carbon has 6 electrons. 2 of them are in the 1s, so 1s2. 2 of them are in the 2s orbital, 2s2. And then we have 2 more left over that have to start filling the 2p orbitals. And because there are 3 2p orbitals that are equal in energy, we don't want to pair them up. We're going to put one of the electrons in, say, the 2px orbital, and one of the electrons in the 2pz orbital, or 2py orbital. It doesn't matter, they're all equal in energy, but we want them to be separated so that they don't have electrostatic repulsion by being near each other when they don't have to be. We have enough orbitals to spread them out. Another minor note for Hund's rule is that those 2 electrons in their own orbitals, those unpaired electrons, both have up spins. So Hund's rule says that if there are unpaired electrons in degenerate orbitals, that the energy optimization says that they should have the same spin instead of counteracting spins. Just one more note there. Okay, and then this we're actually going to see more about in the next section, but I thought I'd add it here just for reference in case it comes up in your homework. Once you get above Z equal to 10, atomic number equal to 10, we can write the electron configurations in something called noble gas notation, where we represent the core electrons as the noble gas that was the previous or the period above the atom we're talking about. So for chlorine, chlorine is in period 3. So we use the period 2 noble gas as our core electrons. So we have neon as our core, and then we have the 3p electrons that neon doesn't have. So we add the 3p electrons to neon to get over to chlorine. So chlorine has 7 extra electrons, 7 more than neon. It has 17, actually, 17 electrons. So 10 of them are in the core of neon. They look like neon, but then we have 7 more on top of that, and they fill the 3s and 3p orbitals like this. Okay, cool. All right, one more little thing to note is that because electrons can have up and down spins, when they are paired, the spins cancel out and the atoms exhibit no magnetic field. So we learned about electrons spinning because they reacted in a magnetic field by splitting into splitting and deflecting up or down based on their spin. That's how we learned about electron spin. But if they're paired up, if we have 2 in the same orbital, then the spin cancels out and they don't. The atoms don't interact with a magnetic field. Atoms with unpaired electrons then, of course, do interact with magnetic fields and produce their own magnetic fields. So let's look at our examples here. So beryllium, if we don't have a magnetic field, we call the element diamagnetic, or the atom diamagnetic. Beryllium is atomic number 4, and it has 4 electrons, so 2 of them are in the 1s orbital, and 2 of them are in the 2s orbital, and they're paired up, so there are no unpaired electrons in beryllium. So all of those paired electrons cancel each other out, and beryllium does not exhibit a magnetic field. Lithium, on the other hand, is atomic number 3. It comes right before beryllium on the periodic table. And beryllium has a full 1s orbital, so it's 1s2 for those first 2 electrons, but then it has an extra one that has to fill the 2s orbital. But that one is by itself because we have a pair in 1s, in the 1s orbital, and then we have one more left over by itself. So that unpaired electron is going to produce a magnetic field and interact with magnets. So we show that by these unpaired electrons interacting with each other. And if it does produce a magnetic field and interact with magnets, we call it paramagnetic. But there's one other term that your book doesn't mention yet, it might mention later, and that's ferromagnetic, which is when you have a magnetic field interacting with the atom or atoms, then those spins, the electron spins, and correspondingly the electron or the atomic magnetic fields, they line up based on the magnets. So instead of being a jumbled mess like they were in the paramagnetic state, they line up, and we call this ferromagnetic. Okay, cool. So this is just a review of our general rules for writing ground state electron configurations. Note, we're still talking about the ground state. I'll tell you when we're not talking about the ground state. That'll be the excited state, and we didn't get there yet. Okay, so for the ground state electron configuration, the electrons should be in all available orbitals of the lowest possible energy. Each orbital can accommodate a maximum of 2 electrons with opposite spins, because they need they need at least one of their 4 quantum numbers to be different, such as the spin. And electrons will not pair up in degenerate orbitals if an empty orbital is available. So this is our p orbital situation. If we only have 2 electrons or even 3 electrons, they will arrange in this way so that they don't pair up, because there are empty orbitals available of the same energy, our degenerate orbitals, for them to fill. So that's what they'll do. And they'll have the same spin based on Hund's rule to minimize or optimize the energy. Just a little side note there. All right, so just to wrap up, let's do some practice. You guys should practice this at home, but I'm going to do sulfur. I'll do sulfur for example. So let's see. Sulfur is below oxygen. So I don't have my periodic table in front of me right now. So let me just draw from memory. We have, so don't worry if you don't know how to draw the periodic table from memory just yet. You don't need to, but we will learn some tricks that help you do that. All right, so hydrogen is 1, helium is 2, and then we've got lithium and beryllium, 3 and 4. Boron is 5. Carbon is 6. These are the atomic numbers that I'm counting. Nitrogen is 7. Oxygen is 8. Fluorine is 9. Neon is 10. Okay, and then from what's after neon? Sodium is 11. What's next to sodium? Magnesium. I'm pretty sure. And then over on the other side, over here in group 13, we've got aluminum. And next to aluminum is silicon. Next to that is phosphorus, 15. And finally, sulfur, number 16. Okay, cool. So sulfur is atomic number 16. That means it has 16 protons. And if it's neutral, which it is, it's a neutral atom. We don't have any charges near our sulfur. Then it also has 16 electrons. So if we have 16 electrons, we need to put them in order of increasing energy. So we start with n equals 1. When n equals 1, we're in the 1s orbital, and there's 2 electrons that can go in there, spin up and spin down. All right, next is n equals 2, and we start with 2s, and there's 2 electrons that can go in there as well. Okay, and then we've got 2p, and there's 3 orbitals there's three 2p orbitals, so that means 6 electrons can go in there. So we're going to fill those up first before we go on to 3s, which has another 2 electrons. So how many do we have so far? 2, 4, 10, 12. We have 12 so far. So there's 4 left. So from our 2p orbital, we can see that there's a capacity of 6 electrons. So there's a capacity of 6 electrons in the 3p orbitals as well, but we only have 4. So our electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p4. So the exponents, they're not really exponents, but these subscripted numbers should add up to the number of electrons in that atom, which is 16. Okay, Cool. So you guys should try that with the other two. So try magnesium and silicon. I did the hardest one. Magnesium and silicon come earlier, so you don't need to fill as many orbitals maybe. I won't give it away, but you should try that on your own and let me know if you have questions. And I'll see you in class tomorrow.